This is June 2012. Question 1. Two factors that affect the severity of electric shock upon the human body. So things like voltage, current level, how long the contact is, the body's resistance, the actual current path that it takes, and the frequency of voltage. They're all going to affect how much electric shock the body gets. If I was going to remember two of these answers, it would be the voltage and the contact duration. Class 1 plug-in heater is designed for use on 230-240. We've got a resistance of 24 ohms and we're told that the power is 2204 and we need to find the voltage. Now you need to transpose the normal formula of P equals V squared over R, and if we transpose that we get V is equal to the square root of P times R. So now that is the square root of all of that times together, not the square root of P times R. That square root should extend across there. So 2204 times 24, all square rooted, gives you 230 volts. C, a single phase fixed wire appliance is operating normally, disconnected. Isolating switch near the appliance has been turned off. When we test for isolation, it's found to be live. So why is that? So it could be something as simple as the wrong isolating switch has been operated, or it could be that the switch is faulty or damaged, the isolating switch, or it could be that the neutral's being switched rather than the phase. D, we've got a three-phase hoist that's operating normally. We've put a new three-phase supply in, and when we test, everything seems okay. Phase goes to phase, neutral to neutral, earth to earth. But when we turn it on, it won't start. And the most likely thing is that two phases have been reversed, and so the phase reversal relay is going to detect this and it's going to stop the hoist starting. So it would be two of the phases have been transposed. E, the output circuit of an auto transformer must be insulated for the highest input or output voltage of the auto transformer. So even if we've got like a 12 volt output on a 230 volt input isolating transformer, that output 12 volt cabling must be insulated to the 230s, because if an auto transformer fails, then we can get that primary voltage appearing across the secondary, and so we need to keep that insulated. So all of the insulation must be up to the highest value of voltage. The term sensitivity in an RCD, so that's just the amount of current required to trip the RCD. So an RCD used in a hospital would be more sensitive than an RCD in a domestic installation. It would require less current to trip it. Test instrument is being used to confirm isolation. Test instrument is good condition. What are we going to do before we commence the test for isolation? So what we're going to do is we're going to do the prove bit of the prove test prove. We're going to ensure the meter is operational by testing on a known live source. So you're going to test it on a 230 socket outlet, power point, make sure that it's reading 230. State one device that can be used instead of a centrifugal switch in a single phase capacitor start. So when the single phase motor starts, we switch out the start winding using generally a centrifugal switch, about 75% full speed, but we could use a current relay, a solid state current relay. We could use an external starting relay, or we could just use a timer. We could say we want 2 seconds of start and run, and then we want that start to disconnect. Describe how the direction of rotation is reversed in a single phase capacitor start. So we're going to reverse the connections either to the start winding or to the run winding, but not both. Or if they're identical, we're going to move the capacitor from the start to the run winding, and the motor will reverse. Generally though, I would be looking at either one of these, reversing the connections to one of the windings. That's part 2, part every electrical installation has a prospective short circuit current rating. So why is it important to consider the prospective short circuit current rating when selecting a protective device for electrical installation? So that prospective short circuit current is the maximum current that can flow under fault conditions. And we looked at that before. It's dependent on the source, how much voltage the source can put out, and it's dependent on the impedance of the circuit. So if it's got a very high prospective short circuit current, we want to make sure that all the devices we put in there can handle that current. So the answer they're given there is the protective device must be capable of safely clearing the level of prospective short circuit current without damage to ensure the protective device can operate within the minimum permitted time. J, what's meant by the inverse time current characteristic? So this is as the current goes up, then the time taken to operate comes down. Question 2, we've got a three-phase star-connected commercial oven, draws 32 amps from 400 volt supply, protected from 40 amp fuse, which is GG, and that's got a utilization category of 1.5. Now as soon as you see that category there, that means that that fuse won't blow until it's 1.5 bigger than its rating. So 40 times 1.5 is 60 amps. We'll keep that in the back of our heads. So as an earth fault loop impedance test for the oven shows a reading of 0.38. While the oven was operating, a fault of 5.6 has developed between the blue phase and the oven frame. So within the oven there's this fault 5.6, and we've got this 0.38 as the external impedance, fault loop impedance. Calculate the total current flowing in the faulty blue phase. Now with this type of question, what we've got is we've got the normal current that would flow, and then we've got the fault current due to that short circuit, almost short circuit, 5.6 ohms connection there. So the fault current is going to be the voltage, which for one phase is going to be 230 volts. So don't fall in the trap of using 400, divided by the total impedance. So we've got the earth fault loop impedance plus the fault. So we've got this 0.38 plus 5.6, which we've got at the bottom there. 230 divided by that gives us 38.59 amps. So that's the fault current that would flow. The total current is going to be that fault current plus the load current. Now the load current is 32 amps. So we've got 38.59 plus 32 gives us 70.59 amps. And that would flow in that blue phase. We're asked to explain using calculations the effect on the operation of the fuse. Now we know that the fuse, although it's rated at 40, it's not going to blow until 1.5 times that 40, which is 60. We've got 70.59 amps flowing, so that is easily going to blow that 60 amps. So fuse will operate as the fault current is more than the fusing current. We've got a second fault now, and now the earth fault loop impedance is 4.84. It's quite high. The same fault, and we're going to see now why, when we've got a high earth fault loop impedance, on occasions the fuse will not operate. So let's have a look at this. Total current, again it's going to be the fault current plus the normal load current. So there's our new fault impedance. 230 divided by that gives us just over 22 amps. 22 plus that 32 only gives us 54 amps. Will that blow the fuse? No, because we said it needs 60 amps. So the total current flowing is going to be 54.03. The electrical hazard to the user, so because it hasn't blown, that fault current is going to keep flowing, and we're going to have a voltage shock at the frame. Now we're going to lose a certain amount of voltage within that fault, so we're going to lose the 22.03 fault current times the fault resistance, which is 123.37. So that the voltage from the frame is going to be 230 minus that little volt drop inside. And so it's going to leave 106.63 volts sitting on the frame of the oven, and so that's a shock hazard of 106.63 volts, which is obviously dangerous. Question 3, we've got a block diagram of a three-phase circuit to a three-phase star-connected hot water cylinder. So there's our hot water cylinder. The cylinder is protected by HRC fuses in the switchboard, and there's a non-lockable isolator and contactor, so we can't lock this off. The existing hot water cylinder is to be replaced. The new cylinder will be installed at a later date. A nice bit of blank page there. So it's saying you've been requested to disconnect the wiring, leave the wiring in place to allow the connection to the new cylinder, and ensure that the area is safe. So how will we isolate the cylinder and ensure it's safe to disconnect? So there's two parts to this, about before disconnection and after disconnection, and they've lumped them all together into this little explanation here. So we're going to open the isolator, and then we're going to test to make sure that that was the correct isolator and that it has isolated. So we're going to test between the load side of the isolator and the supply side to the contactor. So if we know that that's dead there, then we know that it's isolated. You've got to get in that prove, test, prove method. So make sure you put that in any explanation of isolation, that you use the prove, test, prove method. Once we've confirmed it's isolated, you disconnect the circuit on the load side of the isolator or the contactor, and we attach a danger tag to the isolator. After disconnection, the cables attached to the contactor are protected against damage, so you're going to tape them up or put them away somewhere so that they can't get damaged and they can't do damage to anything else. And we're going to put an out of service tag on in place of that danger tag. So that covers 1 and 2. Sometime later, an electrician is engaged to connect the new cylinder. So what's the first thing he's going to do? He's going to make sure that that oven is still, that cylinder is still isolated. And again, how he's going to do that is going to use the prove, test, prove method. The electrician, he's got a multifunction test instrument that has all those. It's got insulation resistance there, so it is an insulation resistance tester. We're going to make sure that it's safe to connect to the supply. So what test can he carry out? Now they've given you in the model answers any one of. So you've got insulation resistance test and protective earthing conductor test. I would always be going for the insulation resistance test. So insulation resistance test, what do we need? We need the insulation resistance test function, 500 volts DC, and we're going to test between each element and the frame of the cylinder. So it's 3 phases, each of those to the frame of the cylinder, and we're looking for 10,000 ohms or more. So not 1 mega ohm, because it's one of these heating elements that we can have a lower insulation resistance of 10,000 ohms. If you want to describe the protective earthing conductor test, then it's low resistance and we're looking for 1 ohm or less. Question 4, we've seen this before in another paper. We've got now 3 fittings, 230 volts. We've got a 16 amp MCB and an RCD, and each lamp is protected by a 1 amp fuse. Fluorescent lighting is not suitable because of the stroboscopic effect. So explain how a fluorescent light produces a stroboscopic effect. So it's the fact that it's an AC waveform, and that AC is going on and off 100 times per second, because the 50 hertz is on for half of that 50 hertz off. So 100 times every second that light is flashing. And if that flashes at the same frequency as the thing is turning, then it could make it look like it's stationary. So how does it produce it? It's because the flashes from the 50 Hertz. What's the dangers? It can make rotating machinery look stationary. How do we eliminate it? Well, we can put different fittings on different phases, or use ballast with a phase displacement, or we mix incandescent lighting, so normal filament lighting, with the fluorescent lighting. How is discrimination achieved in the lighting final subcircuit? Well, we've got 1 amp fuses on the fittings, and we've got a 16 amp MCB protecting it, and so we're going to get discrimination between there. If there's a fault in the fitting, that 1 amp fuse will blow before the 16 amp. Why mustn't the fuses in the light fitting not be shorted out or increased in current ratings? Well, it's probably that the wiring and the components are going to have a much lower current rating than that 1 amp. So if we put, say, a 10 amp in there, and it allows 8 amps to flow, just for instance, then that wiring is not going to be able to handle it. It's not going to be able to withstand high currents that might flow. It needs that 1 amp protection. Number 5, we've got a electrical installation that's completely been rewired. We've put a new switchboard in with RCCBs and MCBs, and we've got a 2 kilowatt heater and a 6 kilowatt range, and both of those have got MIMS elements. So there's that MIMS again. So we're not looking for 1 mega ohm insulation resistance, we're looking for 10 kilo ohms, 10,000 ohms. Insulation is isolated at the main switch. You're going to carry out an insulation resistance test with of the entire installation. So you've got the installation plus those 2 heaters, the heater and the range. So 3 actions that you will take before carrying out the insulation resistance test. So what we need to do is disconnect the MEN link, disconnect the main neutral, turn all the switches and circuit breakers to the on position, and make sure that we've got no loads plugged into the circuits. So you're testing just the circuits and not the appliances that could be connected. How are we going to carry out the insulation resistance test on the entire installation? Well, we're going to bridge out the phase and neutral, and we're going to test between that bridge and the earth. And what that will do, it will test both the phase and neutral to earth. And if there's any connections between either the phase or neutral and earth, that test will find it. We've done this test, and it's got a result of 0.1 mega ohms. So initially you think that's too low. We need 1 mega ohm. But remember, we've got those heaters connected in, those MIMS connected in, so they're gonna make that reading quite low. So we're gonna allow the electrical installation to be certified. So how can we do that? How can we test it and describe it and make sure it's okay? So what we need to do is to disconnect the water heater and the range. So without those in the circuit, we should definitely have an insulation resistance of greater than 1 mega ohm, or 1 mega ohm greater. So we disconnect those, and then we retest the installation without those, and hopefully we get a test result of 1 mega ohm or greater. We then test the water heater and look for a result greater than 10,000 ohms, and then we test the range and look for a result of 10,000 or greater. And if all of those situations occur, then it must be safe. The installation is above 1 mega ohms without those 2, and those 2 are above their required 10,000. Question 6, we've got 3-phase motor with a DOL starter, direct online starter, with thermal overloads. The control circuit is 230, and we've got some HRC fuses, and we need to draw the control circuit. So we've seen this before. Fuse is our stop in series, our start in series with the overload and the coil, but in parallel with the start is the hold-in contact, and that's controlled by the contactor coil. We don't need to show the main contacts of the motor. So the main contacts of the motor would be off of this coil. So they would be controlled and turned on by this contactor coil. The 230 volt coil in the control circuit is burnt out. The only replacement you have is a 400 volt coil. So what kind of modifications are we going to have to make? Well, the 400 volt coil would be okay if we put it across 2 phases. So we need to connect a fuse in the new phase. So both of those phases for the control circuit need to be fused. Connect another phase to the neutral terminal of the circuit. So instead of that circuit going to neutral, it will go to the second phase. Change the color of the neutral conductor to a phase conductor. So basically we're putting across 2 phases instead of phase and neutral. The thermal overload protection is replaced with thermistor protection. Describe how the thermistor would provide protection to the motor. So the thermistor is a device that changes its resistance with temperature. So change the resistance as the motor windings change temperature. The change in resistance operates the thermistor monitoring relay, which opens the motor control circuit. So if we get too much heat in there, then the resistance is going to change, and our monitoring relay will see that change and will open the motor control circuit. The motor will stop. When the start button is pushed on the DOL, starter, the contactor closes, but as soon as the start button is released, the contactor drops out. State the main reason why this situation would occur. Well, it's because the maintaining circuit is open circuit, is not working. So if we look here, we press the start there, the motor comes on because this contactor coil comes in. As we take our finger off this button, this holding contact should hold the supply through there. If there's a break in this circuit somewhere, it won't. And so as soon as we take our finger off the button, this contactor drops out and it will stop running. Question 7, we've got a kiln and we're protecting it with a RCCB and an MCB, sitting on a tiled section of wooden floor. It's been replaced, and during the work the phase and neutral were accidentally transposed at the supply side. So the isolating switch has been turned on. What effect would this transposition have on the operation of the kiln? Well, the kiln ain't going to care which way that phase and neutral comes in, so the kiln will operate normally. What effect would this transposition have on the operation of the protective devices? Again, the devices don't care which way the current is flowing through them, so their operation won't be affected. Potential danger this would cause, well, if we switch the phase but we've transposed the phase and neutral, when we switch off, then the kiln could still be live when the isolation switch is in the off position. We've replaced it again, and we've made another mistake. The neutral and earth were accidentally transposed. So state what would happen if this happened and we turn the isolating switch on. Now the RCCB will trip because it will detect that there is current in that earth, because the neutral current will now be flowing in the earth, and so there will be an imbalance, and so the RCCB will trip. The kiln isolator has been replaced, and during that work the phase and earth were accidentally transposed at the supply side of the isolating switch. So what's going to happen now for C? We've lost the phase to the kiln now, because now we've got the load of the kiln connected to the earth. So the kiln's not going to operate. What about the protective device? The MCB won't operate. The RCCB may operate. I'd have to have a further think about that one. I think it would operate. What danger would this transposition create? Again, the kiln is going to be alive at 230 volts to earth. because we're taking that phase straight to the earth connection, straight to the casing or metalwork of the kiln. So we're going to have 230 volts there all the time. Question 8. We've got an MEN system that we've got to draw. So you must go into this assessment being able to draw this MEN system. Delta to star transformer, 3 phases are neutral. Be able to draw the load of one of these phases through your neutral and your earth bar and your phase connections to a load, and be able to draw in the earth fault loop impedance path. So that's the earthing system. State the main reason why the overall impedance of the earth fault loop must be low. Now we need this to be low so that we get a nice big fault current flowing under fault conditions. With a nice big fault current flowing, we're going to operate the fuses or the protective devices quickly. Just go there. So sufficient fault current to operate the circuit protective devices. So this one, the earth fault loop impedance test is 0.32. It's nice and low. 230 volts. What's the fault current going to be? So it's basic Ohm's law. I equals V over Z because it's impedance. So 230 divided by 0.32 gives us 718.75 amps. That's a big current that's going to operate a protective device very quickly. A MEN low voltage domestic installation is required to have a main earthing conductor. To which parts of the electrical installation are the ends of the main earthing conductor connected? So this comes up again and again. The main earthing conductor, so at one end is going to be the earth bar and the other end is going to be the earth electrode. What's required to be attached at one end of the main earthing conductor? I mean, it's our tag warning against disconnection. Question 9, we've got a 3-phase 250 kVA excuse me, delta star step-down transformer, and we're told that the turns ratio of 287 to 1. The primary is connected to a 66 kV 3-phase supply. The transformer is fully loaded. So remember, this turns ratio is all about the primary values, the primary turns, the phase values, the phase turns and the phase voltage. So when we're looking to calculate the secondary phase voltage, we need to know the primary phase voltage, and because it's a delta connected transformer, the primary voltage here is going to be the same as the line voltage, so it's going to be that 66 kV. So 66,000 divided by our turns ratio, because there's 287 less turns on the secondary, gives us 230 volts. The secondary line voltage is going to be √3 bigger than that phase voltage. So it's going to be 230 volts times √3 to give us just under 400 volts. The primary line voltage is going to be that 250 kVA divided by √3 times VL. Now VL is our 66,000 volts on the primary side. It gives us just over 2 amps. The secondary line current, we're going to use the same formula, but we're going to substitute that voltage for that 398.36. So it's the same 250 kVA and √3 398.36 gives us just over 360 amps. B, why is a current transformer dangerous when we've got the secondary winding left open circuit? If we leave that open circuit, and we've seen this before, then we can get a very high voltage at the secondary terminals. How can we keep the iron losses down in the transformer? Well, the main thing I remember is laminating the iron core, or we can use a special material like Stalloy or silicon steel.